Hello everyone, welcome back to Learn Civil Easy. Today we are looking at a critical requirement in both engineering hydrology and irrigation engineering, designing a weir or barrage on a permeable foundation. When we place a hydraulic structure on soil, water inevitably seeps through the subsoil beneath it. As this water flows from upstream to downstream, it exerts an upward force. If the water exits the downstream end with too much velocity, it begins to displace the soil particles, leading to a progressive collapse known as piping failure. Older models, like Bly's creep theory, assumed water simply followed the structure's base profile. But structures designed using that logic still collapsed. In the 1930s, Dr. A.N. Khosla demonstrated that seepage is governed by Laplace's equation, proving that safety actually depends on a specific hydraulic threshold, the exit gradient. In the next 5 minutes, we will break down Khosla's method, calculate an actual exit gradient step by step, and perform the technical safety check required for your exams. This specific calculation identifies the exact point where a foundation becomes unstable, providing the analytical evidence required for professional design and board exam mastery. Khosla simplifies the calculation by breaking a complex weir profile into standard forms, like a flat floor with a sheet pile at the end or an intermediate point. Because these are treated as independent variables, we calculate the pressures for each section before combining them. Let's look at a numerical problem. We have a weir on a permeable foundation with coarse sand. Dimensions provided: total floor length B is 40 meters, upstream depth D1 is 6 meters, downstream depth D2 is 8 meters. Maximum seepage head, H, is 5 meters. Examiners often include trap data in these problems. When calculating the exit gradient, the upstream pile depth of 6 meters is irrelevant. The only depth that matters is the pile at the downstream end, where the water actually exits the soil. Correctly identifying that we only need the downstream depth is the first step towards reaching the correct solution. Step 1 is finding alpha, the ratio of total floor length to downstream pile depth, 40 divided by 8, equaling 5. Step 2 requires Khosla's lambda formula, 1/2 times 1 plus the square root of 1 plus alpha squared, a standard formula to memorize. We plug in our alpha value of 5. Inside the square root, 5 squared is 25, plus 1 gives 26. Taking the square root of 26, adding 1, and multiplying by 0.5 results in a final lambda of 3.05. Alpha and lambda are the geometric ratios necessary to define the structure's shape before we run the final gradient calculation. Now we apply Khosla's specific formula for the exit gradient, denoted as GE. Substitute variables. H is 5, D is 8. Lambda is 3.05. The denominator, pi times the root of 3.05, gives 1.747. Solving 5 over 8 divided by 1.747 yields an exit gradient of 0.1139, roughly a fraction of 1 over 8.78. This decimal, 0.1139, represents the actual hydraulic force of the water trying to break through the surface at the downstream edge of our weir. Now that we have a calculated force, we have to determine if this foundation will remain stable under that pressure. Khosla established safe limits based on the foundation material. Our specific problem identified the soil as coarse sand. Technical codes provide these safe limits as fractions. For coarse sand, the range is 1/6 to 1/5. Converting these to decimals gives us a safe threshold between 0.167 and 0.200. Our calculated gradient is 0.1139. Since 0.1139 is lower than the most conservative safe limit of 0.167, the upward water pressure is insufficient to wash away the soil. This confirms the structure is safe from piping. Applying the method of independent variables allows for a measurable assessment of soil stability at the point of exit. This approach aligns the design with irrigation codes while providing the specific results required for technical examinations. If this walkthrough clarified the calculation, hit the like button and subscribe to Learn Civil Easy for more engineering tutorials.